Okay, good morning, everyone. Thanks for all of you that have joined in on the webinar. We'll be talking today about resistance weld monitoring and looking at how to improve the throughput and quality of product that you're welding together. Before we get started, I'd like to start off with a brief poll, sort of see what the level of everyone listening in is starting at. So I'll give you about 15 or 20 seconds to go through that and give an answer. Okay, so it looks like there's a lot of people who have already very familiar with the resistance weld monitoring, and some are getting some information. So we sort of expected a range of levels during this webinar, and so we're going to introduce some of the basics for some of those who may be listening in or maybe just getting started, but we also hopefully will cover a few of the nuggets or pearls of wisdom for the more advanced that are listening in today. So let's go ahead and get started. So here we have a picture of a production floor with a number of different operators, a number of different work cells, and each one's working steadfastly at their work cell. Now, as a production manager or as a company in general, you're generally looking for a couple, I'm going to boil it down to maybe just a couple of different key parameters that you're going to be looking for. First one, oops, sorry, there we go, is quality. You want to make sure you have a quality product, and you also want to make sure that you have a high throughput on those. Now, what are quality and throughput, and what really determines those quality and throughput of the product that you're making? Well, I'm going to boil it down to a couple different or three different properties. One is going to be your material choice. The second one is going to be the equipment that you've selected to work with. And then finally, the process itself, the settings that you've set in there. Now, during the course of this presentation, as we're going to be talking about monitoring is really the key to the understanding of those parameters and understanding and being in control of those parameters and ensuring success during your welding process. So during the course of the next 45 minutes, we'll be covering some resistance weld basics in relation to monitoring itself. We'll look at what can be monitored, how we set limits, the types of monitors that are out there and how they're actually used in a production environment. And then what can go wrong and how do we capture that with the monitor itself. And we'll have sort of a brief summary of that initial section about just going over how you're improving quality and throughput. And then the last 10 to 15 minutes or so, we'll look at sort of what we view as the future of process monitoring. And then at the very end, we'll finish up with a question and answer session. So before we begin on the technical portion, just a couple slides on the company overview. We're Amada Miyachi America, and we're founded in 1948 doing resistance welding of dental braces. So that's over 70 years of experience working with resistance welding equipment. And so we have a very knowledgeable base behind us when we talk about resistance welding. Now, since that early time, excuse me, I should also mention, we are a part of the Amada Corporation that has Amada Miyachi. We have a smaller portion focused here in the Americas and have 11 sales and manufacturing offices spread across North and South America. As you can see there below, we have a core technologies, of course, resistance welding. That's what we're going to be covering today. But we also focus in on laser micro welding, micro TIG welding, reflow soldering, marking, cutting, micro machining, glove box, and seam sealers. So we have a wide range of core technologies that we cover in addition to resistance welding. The key industries that we serve today are medical, automotive, battery, and electronics, although we see applications come in from a wide variety of industries and are familiar with those as well. Just to give you a picture of an overview of where we're based, we're not just locally here in North America, we are a worldwide corporation. So no matter whether that equipment's specified here in the US and then goes overseas later, there's always going to be local support for you, whether that goes into Europe or over to Asia or South America. So let's go back to that initial picture where we have the key parameters defining success. Here we have again that work cell, or the work cells set up here. And I want to graph this out in a little bit differently. So we talked about material before, and I'm going to put this here as a circle indicating materials. And really it's going to be dependent on the material composition that, or the alloys that you're selecting, what types of plating that you have, hardness, and the geometry of the material. Second parameter for defining success is equipment. So if I draw in that circle now, we now consider which power supply you're working with, which weld head, what type of electrodes that you have on that. And you can see that it's the intersection of those two where you have the success, and that's going to be material and equipment selection. As we add in the process, now we have the process settings. So the parameters that you're using for the welding parameters, part positioning, cover gas, and so on. And each of those have intersections between the other two circles of success here, where we have optimized settings and monitoring and material control. It's really the intersection of all three of these that are going to determine your welding success. And you can see here indicated, we have monitoring listed because that's one of the keys to ensuring success. So, you might start off and think, okay, I've defined my parameters, I've got my materials, I've got the electrodes selected, everything's fine, everything's going to continue on perfectly, and let's take a look at one of these welds. So here on the top, you see top and bottom, you see a couple of electrodes. The process is dialed in, it's burning off a little bit of plating on the two materials in between. And then the weld starts to form right in the center, right along the interface between the two materials, and giving a nice consistent weld. Well, that's true once you get it set up, but in reality, things change over time. You may have issues that come up where the process starts to change. The part placement, maybe there's a new operator, it doesn't get it in the same place. The materials, you might get another vendor, you get a different grade or alloy that comes in, even though it might be spec'd already for a certain grade, or the equipment itself might change. The electrodes will definitely wear out. The force applied will change over time. That may all lead to issues in your process. Here's a case where things have not gone well, and you see a lot of sparks coming off, and those sparks are, of course, material that's not being present in the weld and going to potentially lead to defects in your welding process. Now, the fundamental question is, do you know where that trouble lies between each of those? Was it the material choice, was it the equipment, or was it the process that led to that defect? What we hope to cover and show you today is that process weld monitoring will help you identify the failure modes and can also be used to optimize the process and also ensuring success from over the course of time. So now I'm going to hand it over to Lauren, and he will cover the rest of the technical side.
We have our power supply on the left-hand side here. It delivers the weld current and weld time. It does this very precisely. We have also on the right-hand side, we have our weld head, which is going to control our force. It's going to hold our parts under force while the energy is delivered to it. This basic setup is the same for fine spot welders as well as your large-scale welders as well. Here we have a basic welding schedule. I'll take you through this. We have a force graph here over the top of it with a timing of the schedule. On the left-hand side here, as the weld head descends, it makes contact with the part, and this is called impact force. This causes a slight ringing of the weld head and the parts. The parts are moving here. As the force continues to build, we reach our firing force. At this point, we enter a squeeze period by the control, and it squeezes to give time for the parts and the weld head to settle. After our squeeze time has elapsed, we go ahead and fire the weld current. Weld current completes its weld pulse, and at the end of the weld pulse, we enter a hold period. At this time, the weld head is still holding on to the parts. It's cooling the parts, and this is where we build our strength into our joint. Key parameters here, again, from the power supply, it must deliver the right amount of current in the right time, and our weld head must deliver the right amount of force in the right time. The timing between the two must be coordinated very properly, very important that we don't fire that energy as force is still building. This causes inconsistencies and can cause expulsion. So our key elements to resistance welding are three parameters that control the main ingredients to our weld are current, force, and time. So how can we ensure that we get that same current, same time, and same force into our part in the correct way? Well, we do that by utilizing a resistance welding monitor. The resistance welding monitor can monitor all kinds of different parameters that are associated with that weld. Some of the electrical ones that we can monitor are current, voltage, time. These are measured values by the monitor. And we also have the power and resistance. Those are calculated values based on Ohm's law. On the mechanical side, we have force, we have displacement, gas flow, or some other input that we can use there. We have some analog inputs on the monitors that we can put many different types of machinery out there. Under displacement, we can detect the presence or absence of parts, so it shuts it off before the weld begins. We can also measure the collapse of that part. So again, the key parameters to our weld success: current, voltage, and time. Below, you see a basic monitor installation. Here on the left-hand side, we have our weld monitor. Weld monitor, one of the main important features of this must accomplish is to monitor the current. This is done using a toroidal coil placed over the welding cable. We also install a load cell into our weld head to monitor the force. And we want to keep track of this welding power supply and make sure it's delivering the right amount of time. And we measure the time from the power supply based on how long the current is actually passing through the toroidal coil. Other things that we monitor here is the voltage. We use a voltage cable that's placed across the electrodes. This monitors the voltage and gives us the capability of monitoring resistance and power as well. We can also place a displacement sensor inside the weld head or bracketed outside. This allows us to monitor the collapse of the weld during the weld process. The monitors are also equipped with communication bus so that we can send all that process data back into our network or into our PC for analysis. The weld monitors also have a discrete I/O on it to communicate with our PLC, which allows easy integration into an automated work cell. So, okay, we saw what parameters we have. Which ones should we monitor? Well, if you have the capabilities to monitor them all, I suggest that you monitor them all. If not, we have a few simple rules below that indicate which parameters you should monitor in given situations. Now, for simplicity, we're just going to keep this to DC power supplies. We're not going to talk much about the AC power supplies. Number one, we have a rule of opposites here. So if we're welding in constant current control, our power supply is set up to weld in constant current control, the output of that current is going to be very precise and repeatable. So what we really want to monitor and take a look at is the variable or the parameter that is not in control. That means if I have a part that's not placed quite right, it's offset to my welding, and I come down and I pass a weld through there, now I'm going to get the same exact current, regardless of how that part is placed. But my uncontrolled parameters will vary, and these are the ones that we'll want to pay close attention to. The same goes if I'm running in constant voltage mode or if I'm running in constant power mode. We want to monitor that parameter that's not being controlled by the power supply. And down here we have some diagrams of different materials and part geometries. Here we have flat-to-flat steel. We want to monitor the voltage because steel is quite resistive, and we're going to have quite a change in the voltage. We want to monitor the force, keep a close eye on that. And then now we have conductive parts here, flat to flat. We want to monitor displacement and power. Due to the fact that we have such low contact resistance here, it'd be very difficult to monitor a change in voltage. We're seeing a lot of projection uses out there today, so in a projection weld, we want to monitor the voltage and we want to monitor displacement. Voltage because we have very high contact resistance at the beginning of the weld, and displacement because we want to make sure that that projection collapses completely. Now, a crosswire weld is similar to a projection in that we have very high contact resistance at the beginning of the weld. So we want to monitor the voltage. We also know that crosswire welding will collapse into each other, so we want to monitor that displacement. So we know what parameters that we're going to use now or that we should use. There's another thing that we need to take into consideration, and that's what limits we're going to set. There's a few different kinds of limits out there. We have peak limits, which are used to detect spikes or dips during the weld. These are min and max limits. We have RMS limits. These are used to measure the average parameter value during the weld. These are generally encompassed across the whole weld, but can be segmented to a certain portion of that weld. We also have what's called envelope limits, and we have a couple different kinds now. We have a segmented envelope limit, which allows us to place multiple segments anywhere along that waveform. We also have our standard limits. It's hard to see that, the one on the bottom, but there's a magenta color envelope there. Standard envelope limits are single segment and can encompass the complete waveform, or we can minimize the time and move it around anywhere on that waveform. Now, when do we want to use an envelope limit instead of a standard peak or RMS limit? Well, we do this when the waveform has a very unique profile. And so let's take a look at this bottom right graph here. We see this waveform, and at about 10 to 15 milliseconds, we see a slight dip here in this waveform. Well, this dip would not be caught by a peak limit, which is up here and down here. Now, this dip would only be caught by an envelope limit because it's changed in its shape. The RMS value might change just a fraction, but too little to be caught effectively with a RMS limit. So now we know what kind of limits that we have and can use. How do we go ahead and set those limits into our power supply? Well, we do this first by performing a DOE, a design of experiments. Here we find out our minimum, our maximum, and our optimum parameter settings. And with those parameter settings, we gain the parameter values of all the other values. And we take all those measurements from those other parameters and throw them into our data processing. We collect all that process data, the current, the voltage, force, displacement, and we compare this to our process requirements, our pull strengths, our appearance, and then we take all that information, throw it into an analytical software such as Minitab, where we determine at that point where we want to set our process limits. Maybe it's 1 sigma, 2 sigma, or 3. Once we have our upper and our lower control limits, we place those into the weld monitor. So now the weld monitor has our limits, and we can back up 1 sec. Okay, sorry guys, we got at the end of this slide, we're going to do another poll. Okay, so I'm going to give you a couple seconds here, 15, 20 seconds. Go ahead and take that poll, and we'll resume shortly. Okay, good. Let's continue. Okay, good. Okay, good. So a lot of you are gauging the quality by pull strength. That's good. Okay, let's continue. So now we have our process limits. So we're going to go ahead and put our monitor into production. We have our resistance welding system over here, power supply, weld head. We're making parts, we're banging away. All that information is going into the weld monitor. The weld monitor, with its limits all set, is making decisions on all that information coming in. It's sending the process data out to the data collection software. It's making decisions good or bad based on the information we've provided with our limits. The PLC is going to take that good, bad information, and it's going to make a decision on what it wants to do. If it's good, it's going to go, obviously, continue to keep welding. If we're no good, the PLC is going to either reject that part or stop the process entirely. Let's talk a little bit about the types of weld monitors that we have. We have our bench type monitors, advanced stationary monitor. These are great to be used for your R&D, your product development. They're great to get the product to market quicker because you can look at all the information on one screen. You can compare and contrast the waveforms. Once you perform your DOE and your validation, these monitors move seamlessly into the production environment. They collect large amounts of data so that you can do your process analysis right there on the monitor or dump that into a collection software. These units are generally dedicated to one machine. Then we have our basic stationary monitor. And obviously the difference between your advanced and your basic stationary is going to be a price delta. The basic stationary monitors are very limited in what they can do. They generally provide just peak and RMS numeric data. There's no large screen to do waveforms, and it doesn't collect the waveforms as well. There is no large amount of data storage on these devices, but they do output the report data from those parameters after each weld. We also have the handheld monitor. Now these devices are very handy. They're great to give to an engineer to take out onto the production floor. You have a bunch of welders that you don't have stationary welders on. You can take your handheld monitor and do daily checks or weekly checks or however you do it in your factory. The checks it can make are obviously it can measure the current, it can measure the voltage, and force at the same time, utilizing a force sensor. This gives you a real bird's eye view of your process, make sure that your force is firing at the same time, correct current and correct voltage. And once he's done all his testing from the units on the floor, he takes that device back to his desk and downloads that information into your database or process software. As this device here has a capability of storing a lot of data as well. And these devices are battery powered, so we don't have to deal with any cords, tripping on any cords. Now the last one here is very interesting, and a lot of you probably don't know this. You say, well, Lauren, why do I want to buy a monitor if I've got a power supply that's already got a built-in monitor? Well, the built-in monitor and most of these controls typically use the control circuitry for the monitoring. So what that means is if there's a unit that's out of calibration or there's a software glitch, that unit might be outputting the wrong current. Even though it thinks it's outputting the right current, it's passing all the set limits, there is a possibility that current is incorrect. So we highly recommend that you purchase either a handheld monitor and do spot checks on that device, daily or weekly, or that you put a watchdog on there and purchase a stationary monitor to keep track of that built-in monitor. So what are we going to use the monitor for? Well, we've talked about it many times during this presentation already, product development. it's a key tool to see all the parameters on one screen and see the correlation between each parameter. Product development leads to product validation. It's a great source to collect all that process information, and it moves seamlessly into the either a manual workstation or into the automated environment. These devices collect lots of data, and they can push that data out for you to store it or archive it. It's capable of capturing serial numbers, so you can correlate your part that is serialized to the data that it was welded with. This is very handy in case you have a customer recall or customer rejected part. You can find that data and to ensure to the customer that it passed all of its requirements. And on a day-to-day basis, we can take that data and analyze that data to make sure that the work cell is staying on track and that the trends are pointing in the right direction. So then we kind of come to the fun part. Okay, I have a problem. I'm getting rejects from my monitor. How do we find what's going on with the weld? What do we look for? This failure mode here is a no weld or a weak weld. We can see over there that this thing didn't weld very well. We have strands hanging off. So this potential cause or identified issue with this is insufficient energy. It could be no weld at all. It could be a weak weld. It could be a nugget that isn't big enough. So the potential causes for these are over here on the left. We have a table here for potential cause and what to monitor for that cause. So we have shunting, where the current doesn't go where it's supposed to go. Some of it goes in the tooling instead of directly into the part. Excessive overlap, mushrooming, or the electrodes getting a larger surface. And of course, we have excessive force. On the flip side of that, we have the failure mode of either being overwelded or getting expulsion. This can be caused on the left-hand side, our cause here, insufficient force, our force timing, part alignments, and pitted electrodes could cause these as well. And the parameter what to monitor is there on the right. I'm going to show you a quick video here I'll let you know what's going on here. We have two pieces of material here, steel, mild steel. This is basically due to the first one there, insufficient force. This is what's not supposed to happen during your process. And you see we had a violent expulsion with material left here on the right-hand side of that video. So yeah, this is caused by insufficient force or could be caused by poor follow-up force. So continuing on finding some process problems using the monitors. Here's a common one. This one is the diagram up on the right. You see the green line there, that's our force line. And the yellow line there is our weld pulse, that's our current passing. So you can see here, obviously, that the current fired well before we reached our force setting. This causes expulsion. This can also cause inconsistencies in your weld. If a customer is experiencing inconsistencies, one of the first things we look at is your force timing. This is accomplished using a weld-through sensor, which monitors the current and force at the same time. Down below, you see what it's really supposed to look like and the adjustments that our customers make after we show them that, hey, you know what, you're firing this thing right there when your force is building, you're going to cause all kinds of problems here. Let's adjust your squeeze time to get that current to fire at the right time. Now, this could be caused just because the customer doesn't know what squeeze time is and how much to give it. It also could be caused by having an air leak in your air lines and causing the cylinder now to get that force up there much slower. That could cause that issue as well. We can protect from having problems using trends, monitoring trends to watch for process drifts. This is very useful in monitoring the drift of, say, a voltage or monitoring your electrodes. Here we have monitoring the peak voltage and peak power. You see at the beginning of this, we have some brand new electrodes here. So the first couple welds here, looks like we're actually declining in our voltage. And this is a factor of seasoning. We're not going to go into seasoning right now, but It appears that these electrodes need a couple hits before they start moving. Here the process is stabilized somewhat. It's pretty flat. At the end, we start to climb. You see the overall rising of this line. Now, as you see here, this is going to continue in this direction. It's eventually going to hit these dotted yellow lines here. That's our warning limits. This is going to indicate to the engineer, A, you're starting to drift. Go ahead and clean your electrodes or replace your electrodes. It provides us with early identification and leads to preventative maintenance before something bad happens. Yeah. We also have sudden changes in the process, a missing part or part alignment. Real quick, we're going to hear the yellow arrow there kind of points to where the problem lies. We can see that the voltage here railed very rapidly. This is caused by resistance climbing quickly. In this case, what has happened here is during the weldment, as soon as the weld head moved, we lost contact with the part and caused excessive resistance, which resulted in here is a catastrophic failure. So improving quality and throughput, how can we do that? Number one, we improve quality by helping guide our product development and product validation. We have our limits set into the weld monitor. This is, gives us a very controlled process. It provides us with data analysis. Our throughput, how can we help that? Reduces scrap by knowing when we need to replace the electrodes before they have a problem. It reduces destructive pull testing, because we know if our limits are right, that we assume that our parts are going to be welded in the correct manner. And it reduces downtime, so by our ability to schedule maintenance. Also provides traceability. So getting back on track quickly. How do we get our process back on track quickly if something goes wrong? And if you follow these instructions, it'll get you back on track very quickly. You have to do your homework. You have to measure and document all your parameter values after validation using the resistance welding monitor. Store those images of the monitored waveforms and compare them in the future if you're having problems. Fill out this process audit worksheet on the right here. It contains nearly all the information you'll ever need about your process. And most importantly, if your process does change and you revalidate, maintain those baseline parameters. And that ends it for my session. I'm going to turn you back over to Dr. Mark Boyle, and he'll continue with the presentation. Thank you.
Okay, hello again, everyone. I'm going to start talking about the future and where we think monitoring is going, and a lot of this will be looking towards what features we think are coming up. But I'd like to know also what features you think are going to be important in the near future. So I'm going to open up a poll again and give you again about 15 seconds to review and answer. Okay, poll's now closed. We'll look at the results now. It looks like we have a fairly even distribution of different thoughts here. Networking quality, prediction of results, and those are sort of the topics that we're going to cover today as well. So here, and I want to tie at the end of this. I'm going to hopefully tie both of these together and sort of show just an overall picture where we think process monitoring is going. So let me click there. Let's go back to that work cell or that production floor again with a number of different work cells again. And I put monitoring in 2010. This could be 2000. This could be 1990. The picture is certainly a little bit older. But what I want to show is that it's independent work cells with each in independent locations. Yes, the operators are side by side, but they're all working independently and they're focused on making their parts. They're not necessarily sharing a lot of the information or passing it along between their neighbors or even the more distant neighbors on there. So a lot of the analysis of what's happening during the welding process is dependent on that operator, and they're watching and trying to make sure, okay, when do I need to change my electrodes? When do I need to optimize the process to get a little bit better weld out? I'm starting to get some issues with my parts, and it's all dependent on that particular operator. Monitor is, right now they're built in, so we have a monitor on each station, and they're providing a signal, as Lauren presented, that is putting out an output saying it was good, it was a good value, or it was a not good value, and discard the part. And Lauren also showed some trending, and so it showed where you could set up a limit for, as the electrodes wear and age and times, that you might reach certain levels, and that the monitors will output that information as well. What it really doesn't do is, if there's a catastrophic failure, or much later down the line, we get a safety recall, or some issue comes up, from your customers that's saying, oh, your welds aren't meeting specs. Well, what happened in that? So that's another aspect to consider. So here's that production floor, 25 different work cells. Let's put a red box around if the system is down, or an orange box if the PM is required. Operator here on cell number 17 says, looks like we need to season or change out the electrodes. Operator number 8 saying, oh, hold on, my machine's not outputting any energy. It's not, the head's not going down. Something's wrong. Something's broken. We need to fix the machine. So really, again, just to reiterate, these are all individual cells. They're supported individually. That requires additional resources to manage and make sure each of those cells are up and running at each time. It's machine and operator dependent, and this can cause longer down periods of time between if that system goes down suddenly, how do they recover from that? And to a large degree, the problems are caught only when they are problems, not before they become a problem, such that that they can avoid that problem or call in for earlier maintenance or schedule that maintenance to come in earlier. So let's take one of those cells, and we have a monitor on that cell. Let's say we make that network capable. That monitor now can put out information. It can put it into, I'm just going to draw a little factory here, and from that factory, although the monitor can do that itself, it can now broadcast that out. And now it can broadcast that out to the team members. It says, oh, cell number 8 is down. We need urgent attention at that location. Or it could also send it out to the manufacturer of that machinery, indicating that field service or customer service, field service might be needed to go in and place a call to say, okay, we see what's happening with the equipment. We recommend you do this and this, or customer service to issue that RMA or to get you new electrodes or whatever the case may be. So now we go back to that production floor with all of these monitors, and we network all of them, and now all that information is being fed into the factory, which is then broadcast out. And so we now have a collection of network cells, and we have one person monitoring all of those cells at one time, indicating and catching when the preventive maintenance is upcoming, scheduling that in, and making sure that you're reaching those or identifying those problems before they're problems. And that, of course, has impact within the business itself. So now, in this analogy here, we have the boardroom here. Everyone's trying to make a decision based on the parameters that are coming in. Factory says, well, I now have a lot of information being fed in from my the production floor, all 25 cells, and the data showing that, okay, the status of each different equipment, the performance, and then the board can now make decisions on how the business decisions, such as product fulfillment or product or material flow to the different work cells. If we know that cell number 8 or cell number 17 is down and needs to undergo some preventative maintenance, and it'll be down for a day, there's no need to deliver material to that certain work cell. Now, of course, these are all drawn such that they're all very close in proximity, but these two work cells principal could be at two different locations, two different levels on the floor, two different locations within a building, or in two different remote locations. And now I want to go through very quickly just some ideas for the process monitoring and sort of tie it in with that idea of networking of these monitors. Now, I think everybody would like to know that in situ, non-destructive testing, on-the-fly measurement that this weld is success or not a success. Now, you'll know, for those of you that are more seasoned in resistance welding, you'll recognize that's not a resistance weld, it's actually a laser weld. So the concept and idea can be applied to any types of monitoring. And of course, today we're focused on resistance welding, but I just happen to have a picture of that in there. Now, if that was unsuccessful, we'd also like to know that was what failure mode led to that being unsuccessful. So let's go back to our Venn diagram. How do we predict success? Well, we know it's a combination of equipment, materials, and process that leads to that success. The challenges that we have are, of course, that there are equipment variables, there are part tolerances, and there's process variation. So each one, and in addition, just material changes as well. And the underlying question is, okay, we can, if everything's successful, it's not as critical, but we want to be able to distinguish between these different challenges, so we can identify what might be the modes that are causing the issue if an issue happens to arise. How do we predict this success? So I change it from how can we to how will we. So what do we need to do this? Well, we need to acquire data. That's what the monitors are there for. But now, which parameters do we need to monitor? Is it voltage? Is it current? Is it force? Is it displacement? Or all of them? How fast do we need that monitor? How fast is that weld occurring? How fast does that information need to be fed back into the machine? And which equipment is needed for that? Do we need toroidal coils, displacement sensors, load cells, and so on? Now that we got the data, how do we analyze the data? There's a number of different ways you can analyze it. We can look for peaks, we can look for RMS, we can look for just overall statistics on the measurements themselves. Now that we have we've measured it and we've analyzed it, what does that mean for the process itself? Those are all the challenges together, and this is going to come, and how we will predict it comes under weld defect classification. So we got to go through a number of different welds to predict that success. So the premise that I'm going to walk through here in the next 5 minutes, or a little bit shorter, is that we know the data that we show right here. So we know what we're putting into the process. We know that what material that we have. We know that how our weld head is set up. We know the equipment, and then below we know which variations that we see in the output. What we'd like to know is, was that last weld good or no good? What do I need to change to bring that back into control if it happens to go out of control? So a lot of this is going to come down to the analysis of the physical signals. The physical signals are what we are measuring: current, voltage, force, time, and so on. So we're going to make a bunch of welds. Here's a couple of electrodes pressing down maybe on some stainless steel, creating that weld right in the center of the between the two materials. We know our inputs of materials, part positioning, equipment condition, equipment performance. And at the output, we're going to measure pull strength, which everyone mentioned. That's probably one of the top ones that everyone judges success. Cosmetic appearance, and we can also detect if there's any spatter or note that there's any cracking as well. And with that, we're going to tie in our time series data that we just measured: current, voltage, time, we might measure that if there's any expulsion, any of those sparks flying off the part. We now label the data such that we take our weld quality measurements, match them up with our time series data, and we indicate, okay, these group over here gave us spatter or some expulsion. These welds here gave us a weak weld, and these over here gave us a good weld. Now we take that label data, we feed it into a machine learning algorithm, and out will come a prediction model. So based on the input parameters that we input to the part, it'll predict whether there was a success or it was a failure at the output. So now we make a new weld, and we're going to measure that in real time. We're going to take the time measurements, get our physical signals in from our monitors, put it into the prediction model, and we'll have at the output our predicted pull strength, appearance, whether there was spatter or cracking, and if we weren't in the good, then what was the failure mode? What was the reasoning? Now, in this presentation, I'm not going to go into any details of how we isolate each of these different materials, but that's sort of the crux, that you have to isolate each of the different parameters and identify what was good and what was bad. So now we're taking all of that information with those prediction models. We have our network cable monitor again. It's monitoring the data, feeding it into the factory. Well, we can do a whole bunch of those all together, and we build up our prediction model. So let's say all 25 of those work cells are making the same weld on the same part, and all those can be used to build up the prediction model based on, well, you could give measuring the equipment, but also process related. Now, there's no reason that you need to do that all in one location, all on one factory floor in one specific location. You can do that on multiple factories separated by, around the globe, and all record that data, build up that prediction model that's telling us whether that weld was successful or not, just by doing that in situ, non-destructive analysis of all of these welds built up. So now, our factory's back in the boardroom. It's now telling, well, the data shows us that, and reports on equipment and process status and performance. So we're added in not just the equipment, but also the status of the process as well. All of those feed into all those business decisions, again, about how material was routed and identifying whether issues have arisen. Again, just to highlight, that would be equipment and process related. Now, this is all just sort of a generalized view of this, of where we think it's going. Network monitoring is approaching rapidly. The analysis is one that's further down the road. So now we come, now we hit the summary, and we're going to have one last poll. What we've covered here, we've looked at some resistance welding basics. Oh, I'm sorry. Let me give you a few seconds to look at the poll, answer the poll, and we'll finish up with a summary, and then we'll open up for questions. Okay. Okay, it looks like we've gotten to the summaries. Yeah, there's a range of different ones, so we'll be following up with you on those. So now, just as a brief summary, we've gone through, and we really appreciate your time today and listening in. First we went through some resistance welding basics, identified the key parameters that occur during a resistance welding process, and I identified how we can monitor those. We identified how limits are set, the types of monitors that are available, and then what can go wrong, and then how are those monitored. We spent just a little bit of time looking at the future of process monitoring, hopefully giving some ideas of what may be coming down the road, and we're certainly interested to know from you as well what you guys envision coming down the road. So as we wrap up, we'll be sending out a email with the presentation link for this here today. We'll be offering, as a thank you for listening in on this, we're going to have a special promotion on any monitors that will be shipping out or purchased by the end of December this month. That will be included in that email.